All right, well, let's get this show on the road. My name is Sherry Sparks. These are my co-speakers, Sean Embleton and Ryan Cunningham. Our presentation today is titled Sidewinder, an evolutionary guidance system for malicious input crafting. I think there's something wrong with the mic here. All right, that seems better. Okay, all three of us were graduate students of computer science at the University of Central Florida. And our talk is going to be about malicious input crafting. We like to make this analogy between malicious input crafting and firing missiles. Traditional black box malicious input crafting, like I'm sure everyone here is familiar with the term fuzzer, is not particularly intelligent. Basically, you throw inputs at a program and you monitor it, hoping for some unexpected behavior or some kind of a crash to occur. Well, it may take a lot of random inputs to be thrown at that program, or a lot of unguided missiles before that program crashes or we actually get anywhere interesting. So the three of us wanted to explore this idea of, is it possible to improve upon this black box fuzzing methodology and turn these unguided missiles into sort of guided missiles? And that's kind of the basic concept for our talk. So I'm going to go ahead and get started here. Pretty basic definition, software vulnerability, taken right off Wikipedia. Refers to a weakness in a system allowing an attacker to violate the integrity, confidentiality, access control, availability, consistency, or audit mechanism of the system. Software vulnerabilities may exist only in theory, or they may have working exploits. And so therefore it becomes important kind of to make this distinction. You can have a program that uses, for example, traditionally vulnerable API calls that are vulnerable to, usually to buffer overflow and such. And, it may not be possible to actually exploit those vulnerabilities. So we have this sort of differentiation between a potential vulnerability, that being a location within a program that contains a known weakness, like a potentially vulnerable API call, and an exploitable vulnerability for which you can actually craft some kind of a working exploit. In order for a vulnerability to be exploitable, a couple of conditions need to be met. The first condition is usually that program location needs to be dependent upon user-supplied input. The second condition, of course, is that location needs to be reachable on the runtime control flow graph. So traditionally in the vulnerability analysis and discovery process, there have been several methodologies that have been employed. The first methodology is your traditional white box analysis. This is also known as glass box testing or structural testing. It simply involves disassembling a program manually, human reverse engineer going through, manually understanding the control flow and the program logic. The benefit is that the human mind is good at pattern recognition. The human mind is more likely to find subtle bugs that a more automated tool would miss. Of course, the drawback is that it's very time-consuming, and time is money, as we all know, so it could also be very costly. Secondarily, it can sometimes be difficult to tell if that potential program vulnerability will be reachable at runtime, and also what is the structure of that input that will allow you to reach that vulnerable location in the program. So kind of the opposite of white box analysis is black box analysis. This is known as concrete box testing or functional testing. Black box analysis does not rely on human understanding of the source or disassembly. It's usually fully automated. And it involves injecting random or pseudo-random input into a program and then monitoring its output for crashes or otherwise unexpected behavior. The benefits of the black box approach is that it's easily automated. And also your vulnerabilities discovered at runtime are definitely reachable, and you know what the input structure was that caused you to get there. The drawback is that the random nature of the input space exploration is going to make your probability of discovering that vulnerability highly non-deterministic. So one common black box tool is the fuzzer. Fuzzers have been used to find a whole lot of vulnerabilities recently, especially in like parser or protocol handling logic. Fuzzers are kind of the definition of black box in the sense that they inject malformed input into a program and then monitor it for crashes. A lot of bugs are the result of programmer oversights regarding assumptions about the structure of your user-supplied input. So these fuzzers are often used to find bugs in parser and protocol handling logic. Some examples of fuzzers that are in use would be Spike from Immunity. File Fuzz was created by the iDefense guys and presented at BlackHat last year. And then Peach Fuzz, which is a framework for building your own fuzzers. Fuzzers they're good tools. They've been used to find a lot of vulnerabilities, but they're kind of a double-edged sword. There's good points and bad points. The good point is the fact that fuzzers are fully automated software attack tools. They don't really require much human intelligence to drive them. And also, the random or pseudo-random input selection results in fairly widely sampling the input state space. And they may generate, inputs that a human might not think of. The bad news about fuzzers is that they're not very intelligent. That is, we keep throwing these unguided missiles, so to speak, at a program and, and hoping that program will crash. But we don't really, over time, learn anything from the inputs that we've tried in the past that would have any hope of driving our input selection in the future to improve our chances of getting somewhere interesting in that program. So therefore, we don't have a good measurement of attack progress. The program, it either crashes or it doesn't. Also, there's a non-deterministic time frame for finding an interesting bug with, throwing random inputs or unguided missiles at this program. So, our program has an equal likelihood of crashing, 2 minutes from now or 2 months from now. So the question is, can we try to mitigate some of these shortcomings of traditional fuzzers and come up with some ideas that can maybe help to create a smarter fuzzer in the future? So our goals on this project were, one, to come up with something that would have a fuzzer enable it to learn from past inputs that it has tried to improve future input selection or to improve input selection in the future. We'd also like to improve the odds of finding something interesting within a reasonable time frame. Obviously, throwing random inputs at a program is going to take a lot of random inputs before you potentially get somewhere interesting or make the program crash. So if we could maybe drive our input selection a little more intelligently, maybe we could somehow reduce the time frame and make things a little bit more efficient. And then, of course, our third goal is to keep the attack as automated as possible. We don't want to revert back to more of a white boxed analysis approach. So the question is, what can we learn? What could we use to drive a fuzzer? We can make the first observation that the runtime execution trace is dependent both upon user-supplied input and the static structural characteristics of the control flow graph for the program. A normal fuzzer, as we said, driven by random input injection, has no knowledge or measurement of how much or what portions of the program and input state spaces have been explored. Perhaps if we had this information, we could use it to choose better inputs in the future based upon what we've tried in the past. A few things to consider. Greater code coverage may correlate to a greater chance of discovering a vulnerable program state. By linking inputs with their runtime execution paths, we may be able to select for those inputs that have a greater likelihood of taking specific dependent execution paths towards areas of the program that we suspect may be interesting or may have some usage of APIs or other types of vulnerabilities. So in terms of input crafting, here's just an example. Say, for example, we have some kind of a packet parsing routine that takes in a packet via the receive function. And following that taking of input through the receive, there's some kind of parsing and validation logic on the execution path. And at some point along in that logic, there are some areas that we suspect maybe, have some kind of vulnerabilities. A simple example being maybe, some string copy out of some data that has been supplied by the input buffer for like a packet or something. So the question is, what does the input have to look like for us to exercise that code path that leads between the receipt of our input from the user through the packet and the and exercising that vulnerable string copy on some code path. So how can we figure this out? Well, we can disassemble the program. We can manually decode the parsing logic. That would be your white box test. We can throw random inputs at it, hoping we will eventually get there, maybe, and hopefully that we might eventually, and that will be your black box test. Or we can try to improve a little bit and use some kind of heuristics or intelligence to hopefully push our program execution towards that state. So maybe we can model this kind of problem as sort of a search problem. First of all, what if we could automatically decode the packet parsing logic? We're throwing inputs into a program, but those inputs need to correspond to some kind of a structure, usually, for it to get past the parser logic. So what if we start out and we don't really know what the structure of that input is exactly? Can we kind of evolve an approximation of it heuristically? That's kind of one question here. And then can we model this input crafting as more of a generalized search problem? That is, in some sense, aren't we searching for inputs that conform to a structure capable of taking certain dependent execution paths in the program control flow graph? Certain areas of the program that we think may be interesting or have a greater than average chance of leading to some kind of a vulnerability. So we have tried to perform this search by driving input selection using a genetic algorithm, where the relative fitness or goodness of a specific input is related to its progress on the program control flow graph. So here's the basic idea. Over time, some inputs will be better than others. How will they be better? Well, one, they may increase code coverage so that they reach previously unexplored areas within the control flow graph. And secondly, they may be on a path to some interesting area that we wish to explore further within that program, where we suspect some vulnerability may lie. So if we take these inputs, these more fit or better inputs, and we mate them of all the ones that we found in the past, then perhaps we can select 4 of those characteristics in the future that maximize code coverage and drive inputs down execution paths past parsing and validation logic towards areas in the program control flow graph that we think may be interesting and we want to explore further. So first, a little theory. I'm going to turn control over to Ryan Cunningham, and he's going to talk about genetic algorithms.
Hello, everyone. Can you hear me? So the theory that is incorporated into Sidewinder is actually, if we were to cover every topic specifically, it could be the subject of basically a whole semester-long graduate course in computer science. So I'm going to try and cover them as intuitively as possible without confusing you. So first, we're going to discuss genetic algorithms. This is what we're using to solve this input crafting problem. So what is a genetic algorithm? It's a type of algorithm that mimics evolution. Algorithm and evolution are 2 words, I think, that people use a lot, but I think don't have a precise understanding of what they mean. So I think we should cover some ground there first to lay the groundwork later before we move on. So what is an algorithm? An algorithm is a specific set of steps to find a solution to a specific type of problem. What is evolution? Evolution is a natural process which acts on a population of organisms. Hereditary information is passed from one generation to the next in the organism's genome, its DNA, its chromosomes. Mutation and crossover, or mating, add random variation to the genomes in the population. So they add randomness to the population. And natural selection removes organisms whose genetic code is less fit to their environment. And with each passing generation, because of natural selection, the organisms in the population better suited to their environment survive, procreate, and presumably the population overall becomes better suited to its environment. And you'll notice that I've bolded some words here. I tried to bold them as much as possible through the rest of the presentation because it'll help you see the analogy between actual evolution and genetic algorithms that try to mimic it. So genetic algorithms, in the most general sense, are what are called stochastic global optimizers. And that's a lot of long words, basically to say that genetic algorithms look for the best solution that they can find, that there's a random component of the algorithm, so obviously it won't run the same way twice, and it finds better solutions with each iteration, but it may never find the best solution, even if you run the program forever. And I'm going to use specifically an example problem here to sort of guide you guys along with a little more practical example. So I'm going to use this problem, the problem of maximizing the number of ones in a binary string of length 10. It sounds like a very simple problem, but it's probably best to start simple. So whenever you're trying to solve a problem with a genetic algorithm, you have to have two things. And these two things are tailored for that specific problem. You have to, and this involves some creativity. You need a representation, that is what solutions to your problem look like, how you're going to represent them. It's genome, if you will. The other thing that you need is a fitness function. This is an equation that operates on a solution and tells you how good or bad that solution is. So in our example, we might use as our representation a 10-digit binary string. I've chosen that. I could choose other things as well, like hexadecimal numbers or something. But here we will use a 10-digit binary string. Our fitness function will be the number of ones in the string. I could, again, choose something else. It could be, I want to, rather than maximizing the number of ones, I could try to minimize the number of zeros. So genetic algorithms, to outline them broadly, I'll go into each one of these steps on their own in subsequent slides. The genetic algorithms work like this. We start out with a population of random solutions, completely random. We calculate each solution's fitness. We select solutions with the highest fitness, mate the fittest solutions more than the unfit solutions, and then slightly mutate the offspring. Once we're finished with that, we've created a new population, which we call the next generation, and we go back to step 2 and repeat this process and iterate basically until we want to stop. So step 1, the initial population. We start out with a population of solution genomes in our chosen representation. And I will be your sort of Steve Irwin or Jacques Cousteau here, telling you about this population of 4 strings, these 4 organisms, binary strings. So we're going to, I chose arbitrarily 4, a population size of 4. There are 4 binary strings here. I chose them randomly, I created them randomly, so we will follow their life cycle. First, we calculate the fitness function for each member of the population's genome. So in our example, we simply go through each binary string and count the number of ones in the string. Step 3, selection. We find out which solutions are the fittest and ignore the rest in our case. So the genomes having fitness of 3 and 7 are the fittest. Another way you might think of this is these guys are the strongest members of the population, or the sexiest members of the population. They're going to have the most offspring. So there they are, the ones with 7 ones and 3 ones. And I warn you, this is a little graphic. We have binary string sex here, so don't freak out on me. So we're going to, in the crossover step, create offspring genomes by randomly swapping their parents' genomes at a random point. So this is the crossover operator. In this case, it's just very simple. We choose a random location. So in this case, we chose randomly 3. And all we do is flip. So 1/2 comes from one parent, the other half from the other parent, and vice versa. So now we have 2 new offspring. Our population size was 4, remember, so we need 2 more to round out the population. So we repeat the process, this time at location 6. If we continue doing this, unfortunately, it seems really nice because we're always taking the best, but eventually we're going to converge to just a few that are all basically identical in our population. The problem of inbreeding comes in here. So you have to maintain variation, randomness, and that's what mutation does for us. It injects more variation into the population by randomly flipping a bit with a certain low probability. Now, all of these steps in a genetic algorithm have parameters basically you can set. You have lots of options, so there's no hard process for creating a genetic algorithm. It's kind of an art. You have to tweak parameters and see how you do. So in our example, we flip bits at random in the offspring that we generated, and now we have a new population. Step 5, go to the beginning, repeat. Our population has all grown up, and now they're just like their parents. We calculate their fitness and move on from there. If you notice, the population's fitness overall went up. This conforms to our intuition. You know, genetic algorithms are optimizing. They're trying to find a better solution. So I told you there were certain parameters for each one of these. One of the things that you have to sort of find a balance between, strike a balance between, is mutation and crossover rates. The goal, or what you're striking a balance between, is preserving existing information and generating new information. Crossover preserves information in the population, but mutation generates new information. It's generating new information at the cost of destroying what you've already learned. So a high mutation rate and low crossover would correspond to an aggressive global search of this, almost brute force search, if you will. A low mutation rate is less aggressive. You're exploring a very small area of your search space. So I told you that there were two things that we need anytime we want to use a genetic algorithm for a specific problem. We need a representation. So in the problem that we're trying to solve here, the input crafting problem, we need to decide what inputs we're going to inject. How are we going to describe them? The other thing is we need a fitness function. That is, how are we going to measure how good an input is? So our representation, we need to inject input in a certain format. We don't just want to throw binary strings in arbitrarily, because that is a very, very huge search space. So our representation describes the steps used to build the string. Rather than the actual string itself, we're not operating on the string itself, we're operating all of the crossover and things like that, or operating on a specific set of steps to create the string that ultimately we input into the program. So to do this, the rule set that we use is a context-free grammar. This is a grammar for, it is a way, grammars are a way of describing languages. We all know that sort of intuitively. Context-free grammars are a formal grammar, which means that it's mathematically precise. Context-free grammars consist of terminals, which are ultimately the things that are actually in your language. If we were talking about terminals in English, we would be talking about words, everything that I've said in the whole presentation, etc. Non-terminals are placeholders, sort of like variables in algebra. If we were writing a grammar for English, again, we would talk about nouns and verbs, adjectives. Then we have production rules, which are substitutions that you're allowed to make for each non-terminal. So, for example, in a noun, you could substitute a specific noun: man, dog, cat, computer. The initial rule is the first production rule. It's just a production rule like all of the rest, but you start from there. The process of generating a string begins at the initial rule and proceeds until there are no more non-terminals in the string, no more noun and verb. We actually have a specific sentence: the man ran. So this is an example in sort of the standard textbook format way of writing grammars. So normally you write terminals in lowercase letters. So lowercase c, lowercase d, lowercase e, lowercase s, lowercase x. These are all the things that are actually in the language that this grammar is trying to describe. The rest are just variables. These guys are written in capital letters. Again, this is just tradition. So the non-terminals in this case are bold capital letters. Each one of these on the left is a production rule or a substitution rule. And this means if you see this non-terminal in a string, you can substitute it for any of the rules that are to its right. And again, by tradition, normally S corresponds to the initial rule, and that's where you start. So I'll try and make this, again, a little more explicit by giving you an example. So we start out with our starting rule. We can substitute for S either S, capital A, lowercase s, or lowercase x, capital B, x, or a lowercase m. So I will just choose one arbitrarily. We choose x, b, x. For the b in that, because it's a non-terminal, we can substitute again any of the things to the right of b. So we have three options there. We substitute again the first, and we repeat this process again now, substituting for the a. Now we'll substitute for the b. And finally, for the c, we substitute one of the three and end up with all lowercase letters, or all terminals in this case, which means we're done. We've created a string in the language that this grammar describes. So a grammar is a description of how to build all possible input strings, not a specific one. It's a description of a whole language. GA operators are not good, or GA operators are good for integer strings, but not like operators, not rule sets. This is, I described to you that we're dealing with binary strings or integer strings. In that example that I used, the binary strings. How would you do that on a rule set? That doesn't even make sense, really, does it? So how do we use a grammar to build a string that's actually in this language specified by this grammar? Or for a very specific example, how do we turn the integer string 10247 into that specific set of all terminals? And we're guaranteed that it is actually in this language described by the grammar. So we use a process called grammatical evolution. So to produce a string from our grammar using a series of integers, we use grammatical evolution, which can be summarized in the pseudocode. So while there are non-terminals in the string, just like before, we don't stop until it's all terminals. We find the first non-terminal from the left in the string. So we'll define num rules here just to have an abbreviation. It's the number of production rules for that first non-terminal. So if it was A in the previous slide, I think it had 2 production rules. Just a simple number, just an integer. So we take whatever the next integer is in our genome. We just go down from left to right, our genome. And if it's a 1, 2, 3, we just mod by the number of rules and apply that production rule. So again, I'll give you a specific example. So we start off as first we number each one. And I'm indexing from 0, just to make it more explicit. So we start with S, the non-terminal S. We're going to apply the first production rule. So we're going to substitute 1 mod 3 is 1, obviously. So we substitute X with the first production rule. 0 mod 3 is 0. And 2 mod 2 is 0. And we continue down the string until we reach the end, and now we have a string in the language. So now we have the representation, which is grammatical evolution. We solved that problem. The other thing we need is the fitness function. How are we going to measure how good the input is? Remember that problem. So we can observe the program's dynamic behavior. When we put an input in, we can watch what happens with the program and judge how good our input was based on the static control flow graph. We want inputs that maximize code coverage. In other words, inputs that cause previously unobserved behavior. In other words, inputs that go places on the control flow graph previous inputs haven't explored. So what are we going to use for this? We're going to use a statistical model. Statistical models are handy for explaining what we mean by rare or expected or unexpected in a quantifiable way. You would use a statistical model here if you own the casino to find out, the expected earnings that you would have. Obviously, you wouldn't want a game where it is exceptionally rare that someone loses and they walk away with all your money. So there's a particular type of statistical model called a Markov process that is appropriate in this case. But rather than bore you with theory because it's statistical theory and I think everyone would go to sleep, I'll just try to show you how it works. So during a generation in our genetic algorithm, we keep a running total or sample of the solutions that use each transition in the control flow graph. So that's just from a particular node, how many take one edge versus another. So in this example, you can see I sort of labeled just on this control flow graph lots of probabilities or ratios. To compute the fitness of a particular solution, we calculate its probability, and we're assuming a Markov process. I know only statistical people would even care about that. So let's not go into that. So let's say a particular string follows a path down this control flow graph, A, C, E, D, G, M. Its fitness would be its probability, so all we do is calculate the probability, and all you have to do that is multiply the total number of the total proportion that took that execution path. So in this case, we do that, we get 0.18. So as you can see, the lower the numbers on each edge that you take, so the less that place has been explored, the better your fitness is. So now we have the two things we need. We have a representation, grammatical evolution, and we have a fitness function, the sampled Markov process. So now that we have those two things, we need a specific implementation, and that's what Sean is going to explain.
We're going to go ahead and plug in the laptop so it doesn't die in the middle of the presentation. Hi everybody, my name's Sean. Thanks for coming to our talk. I'm going to dive into the implementation part. No more theory. So the first thing we need to do for the implementation is to extract the subgraph of the overall control flow graph that includes all the nodes existing on a path between what we're going to choose as our source and our destination. To get the entire control flow graph, we're using IDA. We wrote a little plugin to spit out the control flow graph. And then we're going to squeeze in on it as far as what we're interested, the part we're interested in. One thing to point out is the rejection set. We're going to identify rejection nodes because those are going to become important later on when we want to short circuit a genome. Once it reaches a point that it can no longer reach the destination, there's no reason to continue executing it. And we have a little image coming up here. So first of all, if we consider a really simple program, very simple, and say this is the control flow graph for it, and these are all the nodes. Say we identify the source, which could be the receive we talked about earlier, and then say we see a vulnerable API call, such as a string copy. The next thing we want to do to trim down the control flow graph is to find all the nodes that are on the path or on any path from that source to the destination. So we did this using a little bit of modified depth first search. So now we see what we're interested in mostly is the path nodes, and those are all the nodes that are reachable from the source on the way to the destination, so we can track progress of the genomes that are in the population. Now another thing we're interested in is going to be the rejection nodes, and you can think of the rejection nodes as sort of a fence around the subgraph that we're really interested in, because if anybody tries to go outside of the fence, we don't care about them anymore. So we're going to get rejection nodes. Basically, the way we did that was just look at the nodes that weren't on a path and then iterate through the nodes that were on a path, and if there's an edge going to that node, it's a rejection node. So now we have a subgraph that we're interested in mostly, which is the source, the destination, all nodes that are on some path from the source to the destination, and then the rejection nodes, which we'll talk about a little later again. So now, what we want to do when we have the graph we're interested in, the subgraph, we're going to place breakpoints on all these node addresses. Sidewinder is going to run the target application inside a debugger. So as it pushes each genome through the execution, when the debugger hits that node address, it's going to pop up and call a little subroutine that's going to do it's going to keep some information about where it's going. So, like I say, the breakpoints are used to evaluate progress. What we do is we'll run the genome through the target application. And as that genome hits nodes that have breakpoints on them, we're going to track it. For each genome, we're going to keep a history, the path history that it's taken through the control flow graph. So as long as it continues to hit nodes that are on path nodes, we're interested in where it's going. So we're going to keep adding those addresses into the path history for that genome. Now, if that genome hits a rejection node, it's no longer capable for the node to reach the destination. There's no path from a reject node back on. So we're no longer interested in keeping track of where it's going. We'll just go ahead and short circuit it and move on to the next genome in the population. And I think that's what it says basically, when destination is determined to no longer be reachable. If we haven't reached the target, we're just going to kill it and go to the next one. And here's a little illustration to continue from the last time. We see the subgraph we're interested in, the source, the destination, the on-path nodes, reject nodes. We're just going to simply place breakpoints on all those. And that's really all we're interested in during the execution. So once we have that subgraph that we're interested in, it's just a matter of running Sidewinder. And just to recap, it's going to start with an initial population of some amount of genomes. It's going to push each genome through the execution, through the control. It's going to execute it through the target application. It's going to track it as it goes. As it hits those nodes, we saw how the fitness, as it hits nodes, it's going to build a history path. And another thing we're also going to do is, as those nodes get hit, we're going to keep a visit count. That visit count is what's going to be used to calculate the fitness once we run all the genomes through. So those numbers that we saw, the percentages, 75 took this path, 25 took that path, all that's done while we're actually executing genomes through the application. So once we run them all through, we'll go ahead and calculate the fitness. So for each genome, we'll just look at its path history and just calculate its fitness as it goes along for whatever, how far it made. Once we have that, we're just going to go through, look for the best genomes, the most fit, and then we're going to do the GA. We're going to cross them over and mutate them and build a next population and just continue doing that over and over until we hit the target destination node or whatever the goal happens to be. So we're going to give you a little demo because those are more fun to watch. We have two little demos. Two little target application. One is a key validation, a simple little key validation. It's a little crack me written by Harlequin. Now all it does is take in a 10-digit key and you press a button and it says yes, the key is valid, or no, it's not. As far as, thank you. I'm going to talk about a few things. I'm going to describe the application before we actually run the demo so you'll know what's going to happen before it happens. So that's all that target application does is it tells you, yes, you found the key or you didn't. The goals for Sidewinder in this case, we just need Sidewinder to find a valid key. That's all we wanted to do. So we have to pick a source and a target. And this is a very small application. It's written in assembly. So the source is just going to be the node that handles reading in the key from the text box. And we're going to choose the target destination node to be the node that handles popping up a message box, yes, you hit the node, no, your key's wrong. Now the grammar that's going to be imported for this one consists of terminals that are all printable ASCII. They're lowercase alphabet, uppercase alphabet, 0 through 9, and then some other valid window file name characters. I think there's like 94 characters. So the grammar has 94 terminals, and it's an ASCII grammar. So what it produces is going to go straight into the text box, and we're going to go ahead and press enter and see what happens. So we'll go ahead and pull this one up so we can see what happens. First thing it's going to ask is for the target application, the graph description language, which is the subgraph structure and everything, the grammar, and it's a process in this case. So we see the GUI come up. In the top left, we have some GA settings. It's just for all the theory stuff. What do you want it to do? Refine it. And then we have over here, we have a little, in the bottom left, a log window. The interesting window is that best genome window in the top center. What that's going to do is for each population, after it's done calculating the fitness for each genome, it's going to pop up the top fitness genome in there. Now, if there's multiple genomes with the same fitness, it's going to randomly choose one. You will notice that they'll pop up in black. If you get a red string up in the best genomes, that means that particular genome made it somewhere further in the path. So it's done something good. It's going to be rewarded. It's going to become the top genome, and it's going to get a breed with everybody else, depending on some of the GA settings. If it prints up in blue, that means it made it to the target. So we go ahead and we choose a source node and a destination node, and we're going to see the graph pop up. In this one, we show the graph because it's small enough to put in there. In the next demonstration, there's over 1,000 nodes or so, and we don't have it working with the graph yet. It's like 750 megabyte graph file. So if you look at the graph, you see there's the target, the source that we chose, the destination. Those are all the nodes that are on some path, and that's sort of the control flow. So once we have that, we go ahead and press play, and you're going to notice best genomes popping up right away. As it hits the node, it's going to color it green, so you can kind of track its progress. Now up front, there's just some random stuff happening. The interesting part of the structure, the validation logic, is in this linear bottom part. And what you'll see what happens here is, if I pause it and you look in the best genomes window, you'll see the first thing to let you in, I should have told you this key validator, the validator steps are basically like this. The string needs to be length 10, the first character needs to be a 4, and then the next 3 characters need to be an interdependent sequence of characters based on some Boolean operators. And then the next 4 characters have to be 4, 5, 6, 7, and the last 2 characters have to be 0, 3. These last 2 0, 3s are brute force, and that's going to make a big difference because there's really no information to be gained from that. So it takes a little longer to brute force. But brute forcing 2 characters in a 10 string is a lot better than brute forcing all 10 of them all at once. So we continue on and go ahead and pull up the actual target application so you can see the genomes are actually they're actually being pushed through there. The next thing it's going to be trying to do, it got a string of length 10, so the GA is going to remember that. It's going to say, okay, we got to that node with 10, so we've learned that, we want to remember that, and that's kind of the intelligent part. Next thing it looks for is a 4, which it hit a 4 there, and now you see all the best genomes have a 4 as they continue going. After that, it's going to continue pushing, and it hits the next 3 characters, which are that interdependent relationship. Once it does that, the best genomes are going to remember that, and they continue pushing forward. The next thing it's looking for is the 4, 5, 6, 7 sequence. But what's interesting is because the second, third, and fourth character, they're interdependent. There's multiple combinations of them. So every now and then a mutation operator will mutate one of the genomes and just hit upon 3 different characters. And if you look in there, you'll see, for instance, 3 characters are staying the same, and then there's a different one that'll pop in. But that's another valid string. So it'll continue going on here. It's going to look for the 4, 5, 6, 7. I'm going to fast forward a little bit. Say up to here. So now if you look in the best genomes window, you see there's a 4, 5, 6, and it got the 7. So it's made it almost all the way to the target. You see the green nodes are all the way to the target, except for that very last node. The validation logic on that very last node is the 0-3. The two characters have to be a 0-3. It's just one comparison in one node, so it's a brute force link too, which takes a little longer. Basically, it's reducing to a brute force search now. But like I said, it's better to brute force on just 2 of those 10 than all 10. On average, it should take less time. So if we look at it, it keeps going. What will happen eventually if it hits it? Okay, at this point, this genome, there has been a genome that found it, probably mutated the 0-3. And if you look, you'll see that genome has listed in red, which means it made it additionally further on the path, and it's also reached the target, so it's also in blue. So there we have a valid string, a 4, 3 combination, and then the 4, 5, 6, 7, and then the 0-3. So Sidewinder was able to successfully evolve a string to pass this key validation. And it did it in a relatively short amount of time when you compare it to what a brute force search of 10 characters, each of which can be almost 100 different characters. So you're looking at like, what, 100 to the 10th? And this didn't take very long. It does run a lot slower in this recorder program, I've noticed, and it shakes the graph around. So it actually runs, probably it could do this in maybe 5 minutes, 5 to 10 minutes, whereas the recording is like 20. The recorder stops the execution and takes snapshots, I guess, of the screen. So that's that one. Let's go ahead and get out of there and take a look at the other target, which is a little more interesting. This target is a TFTP server. It's called TFTP 2000. It's available online. You can download it. There's a little bit of information. It does have 2 string copies in it that are vulnerable. It's already been shown that those are vulnerable to buffer overflow. So it makes it kind of an interesting target. Plus, it's a real-world TFTP server. I think it's pretty widespread use. I don't know why, because it's got those vulnerable API calls. So it's a simple server. It listens on the network. It accepts packets. It's going to try and parse the packet to see if it's a valid request, and then it's going to service the packet. The goals here for Sidewinder are twofold. We know that it has the vulnerable API calls, the string copies. Those are documented. So we're interested, maybe we can hit those string copies. Can we reach them? Can we get to them? The second goal, which is also interesting, is can Sidewinder evolve the packet structure of a valid TFT packet? Now, the grammar we use for this program is a little bit different. Since we have to send packets over the network, we need to be able to represent bytes, like a 0, a 1, a 2, a 3. You can't do that with printable ASCII because a 0 is like a 74, I don't know, it's somewhere in there, 23. So the grammar is a bit different. This grammar will produce groupings of 3. It'll produce 000, 001, all the way up to 128. It has 128 terminals plus 2 extras. Once that incoming string comes into Sidewinder, it's going to group it off by 3, convert it to an integer, and put it in an unsigned character. That's going to build the packet that it can fire over the network. And that way we can represent bytes, which are required because the TFTP packet protocol specifies that you have to have bytes as delimiters. And the opcode is also, a byte. So for this program, the source and the target, we're going to put the source right on the receive, because that's where we're interested in start tracking it. We're going to choose the destination node as a node that's right after all the validation logic. So right after it's determined that there is a valid packet, and the TFTP server would then try and send a reply. That's where we want to try and get at this point. I've talked about the grammar is a little bit different, so we'll go ahead and fire this one up and see what happens. Again, we're going to have to choose the target application, the graph, and the grammar. In this case, we're running a service, so we need to tell Sidewinder it's a service so it can start that service up. It's a little bit different to start the service. Now this program, go ahead and maximize. This real world program is a lot larger. It's got, you can see all the nodes in the drop-down list here. Almost 1,000 nodes or so. So it does take a little while longer to build paths and set breakpoints. Even though the depth first search is pretty fast, it still takes a little longer. And we've disabled the graph, excuse me, because again, the image file is just so big, it can't scroll and stuff. But it's still going to do it. It's going to set all the breakpoints here, and then we go ahead and press play. Once it starts going, the validation, so you know ahead of time for this TFTP, is there are 5 valid TFTP packets. The shortest one is an ACK. I think it's 2 bytes opcode and a 2-byte sequence number. So this particular server, the first thing it does is check for length 4. Once the packet's length 4, it's going to check for a valid opcode. Go ahead and pause it. Once it sees a valid opcode, it's going to go ahead and check for some sort of character string, which is a file name. That has to be terminated by 0 byte, and then a transfer mode string, also terminated by a 0 byte. And we see it already started up here, and it's hit the beginning stuff. Every genome is going to hit the receive, so that's a given. So the first thing it's going to do is try and find 4s, length 4. These best genomes, 3 characters represent 1 byte, so 12 is actually length 4. And it's going to go on, once it is, and it's going to try in that order. It's already found a packet that's length 4, so it's looking for valid opcodes. So I'm going to go ahead and skip forward. This one runs a little slower, mainly because the receive is not working right now, so we have to sleep. If we go up here, say, I don't see anything interesting in the window there. Okay, this packet now, if you see that, oops. This packet that's in red, this genome has made progress. And the reason it did so is because if you look at the first 2 bytes, it's a 03. That's a valid opcode. I think it's a data or an ACK. So now Sidewinder's figured out a valid opcode. It's going to continue to use that knowledge and create mostly input strings that already know that, so it doesn't have to figure it out again. So you see a lot of the best genomes continue to be valid opcodes by all the 003s. I guess there it just found a different opcode, a 2, which I think is a write request. And that genome hit further in the path. Over here we have what's a little interesting. We keep track of the code coverage. So just so we know, how many of the nodes we've been hit from the subgraph that we're looking at. So it's found an opcode. It's found an additional opcode. It's found 2 opcodes now. And it's still looking. What it's trying to do now is reach further into the graph, which is the file name, terminated by a null byte. And eventually it will get that. Let's see. Okay, we have some more here. It's on a write request or a read request, which is a 1. So if you see 0s and then 1, that's a read request. 0s and a 2 is a write request. There's a bunch of random characters in there. And then if you look in the middle, I don't know if you can see that on these slides, but it does have random characters, and then it has a 000, which is a terminating null byte, which means it's found an opcode, some random file name, and a null terminator. So it's gotten almost all the way through a valid packet. The only thing it needs to find now is put in a transfer mode string, like netASCII or octet, and then a final terminating null character. And then it's found its target, and it's managed to create a valid TFTP packet. One of the interesting things to note is the grammar that we fed into this doesn't have any information encoded in it as to what a valid TFTP packet looks like. All the terminals are just bytes. So Sidewinder is actually learning what a valid TFTP packet looks like. And it's continuing to fire those into the program. So we fast forward a little more. And it plays with the length. It changes the file name strings somewhere right around here. Okay, so blue again means that some genome has reached the target. And it's switching back and forth between read requests and write requests. And then there's a file name, there's a null terminator, and there's some transfer mode string, and then a null terminator. So all these blue representations are valid TFT packets. And you start to see a lot of them pop up. What's interesting is once the population will start to converge. So all the genomes in the population will start to converge upon valid TFT packets. And the structure is maintained for the most part, except your random mutation. The structure is maintained. What's changing here is the file name is changing, and the transfer mode could change, but we put those in the grammar, and that one's over. Because we know, obviously, we're dealing with a TFTP server. We know that we need those terminals in there. That's just a gimme. So those are two demos we have. The first one is that little crack me, and the second one's the TFTP server. It seems like Sidewinder is doing a pretty good job. It found a key for the key validator, and it successfully formed valid packets, and it was able to hit the target, which means it also passed through those string copies. So it's passing through those vulnerable calls. So we might do something with that. Maybe we want to get to them and play with them instead of just going straight to the target. And we're going to actually touch on that here in a little bit. So we'll get back into the presentation. I'm going to talk about some of the advantages that we think Sidewinder offers. First of all, we're applying knowledge gained from previous experience to drive our choice for future inputs. And that's, instead of just unguided missiles, so to speak, and creating stuff and just firing it in and see what happens, we're actually remembering, okay, we got this far with this opcode. Let's keep that and just see, it got us there, so we'll keep it and we'll keep going. We'll use the knowledge we have gained. See if we can continue to get further and further. This is well suited for parser type code. There's a rich control flow structure, and that's great for the GA. It thrives on that. Another advantage is we have minimal knowledge of the input structure. We don't need to know what is inside each node. We don't need to know what the logic is. For instance, in CrackMe, the 3 characters that are interdependent on Boolean operators, we don't care what that is. We just need to know when it leaves that node what edge it takes, because that's how we're going to determine the fitness. So we don't need to know anything about that. In the GA, we've seen that it can learn to approximate the input. Another big advantage is once a target location has been reached, Sidewinder can, if we let it run, like we did on the TFTP server, it will continue to produce additional varying inputs that are capable of reaching that target. It kept spinning up more and more blue strings. They were all valid TFTP packets. They varied with file name, but they were all getting there, and it'll just keep doing that forever. Of course, there's limitations. We all love limitations. One of the main limitations we have is we have a difficulty in extracting parts of the CFG, the control flow graph of the target application. So we're using IDA, so that's the static disassembler. So we see, I'll call EX, which is going to call, right, the target address is in a register. Well, since it's static disassembly, we know that we don't know what that address is until runtime. So we really can't put an edge there. We don't know where the edge is going to go. So that's a limitation right now. We have to try and work on that. Another thing is, Sidewinder, because of the GA, it's very dependent on the control flow graph structure. The target program, the target application, must have enough information embedded in its structure for the GA to learn from. And an example here would be that key validator. It's a 10-digit key. If there was only one node that just did a string copy with a 10-digit key, that's just a total brute force. I mean, we can't learn anything. There's no control flow. So the program has to have control flow for the GA in order to learn and progressively get closer and closer to the target. So it's not going to be useful for programs with a flat structure, you know, like a straight up string compare for the whole thing. And another limitation we have is we can prove that we can reach a target destination node if we get to that destination node. And that's nice. We can say, yeah, there's a vulnerable API here, a string copy, and we can get to it because we reached it. So we reached the target, we say, yeah, we can get to it, now can we do something with it? But on the other hand, if we don't get to it, because of the random nature of the GA, we can't say that it's unreachable. So Sidewinder could run forever. It may, by some incredible odd, never hit it. We can't say that it's unreachable. You could still get there. So it's still, if you're trying to do some kind of check and say, oh, well, this program's safe because you can't reach that, Sidewinder is not going to be able to tell you that. Because if it can't reach it, that doesn't mean that you can't get there. So that's another limitation. When we look at some of the conclusions, what we think Sidewinder offers is we think we show how genetic algorithms can be applied to the input crafting process in order to maximize code coverage and intelligently drive a program into potential vulnerable states. That's kind of self-explanatory. Also, it's mostly an automated approach. Again, it treats the internal structure of the node as a black box. We don't care what's inside that node. We don't care what the logic is. We just care where we went when we left it. The most unautomated part is choosing a source and a destination. And we're looking at ways to automatically do that. As a side note, we were thinking possibly we can search through the program for all API calls, pull up a list, let the user select which ones it's interested in reaching, put those into a target group, and then iterate through targets and see if we can hit one as we get there. And another conclusion we have is Sidewinder. We think Sidewinder represents a first step towards exploring ideas which may create a smarter fuzzer, as opposed to just, you know, creating input and firing them in and see if we get a crash or whatever. We're going to try and reduce the time and do it more intelligently. We do have some future work ideas, and I think I gave one of those away already. We do need more vigorous testing, of course. A program is never done being tested. There could always be bugs. This is theoretical so far. That code, that Sidewinder you saw is really just a proof of concept. You know, we've just been working on it since we have the idea for a few months, and that's where it's at. It obviously needs more work, and we need to test it on more and more programs, you know, so we can learn what else it needs to do. It does work pretty well. It does find a key for the key validator, and it does craft valid TFTP packets. It is capable of reaching the destination, so that's pretty good. Another thing we want to try and do is improve the grammar. I'm not a big grammar guy, but what I was told is we try to evolve the grammar rules themselves. The grammars that we import now are hard-coded grammars. So the non-terminals go to terminals, but that's hard-coded in. So what if we could evolve the grammar rules as it was running and create new grammar rules? So we can maybe reduce the amount of terminals that some non-terminal can go to. If we can do that, it's going to make it more efficient and, you know, get to where it's trying to go faster, hopefully. Another thing, the idea we had was maybe we can dynamically refine the grammar rules. So if we're running a genome through a target application and it hits a breakpoint, maybe we can go look at registers or memory addresses associated with that and see if there's any interesting strings stored there. And if they are, maybe we can throw those into the grammar. Maybe it was a string compare with something, with a string that's at an address stored in a register. If we can pull that string out and throw it into the grammar, maybe that'll be good. Another thing we want to talk about is target triggering. So what happens when we reach the target? In the first demonstration we saw, the crack me, we reached the target, we got a little message box, congratulations, you found a key. That's great, you know, it stops running. But what if we can do more interesting stuff? What if we can set a target that's, say, a vulnerable string copy call, Okay, we got there. That's good. We know how to get there. Now let's see if we can hammer it and exploit it. Let's see if it's exploitable. So maybe Sidewinder will switch modes and say the fitness function, rather than awarding fitness for traveling further down the path towards the target, maybe the fitness function becomes, well, you're going to get higher fitness if your string grows longer. So now the inputs are getting to that string copy, and we're going to start growing the string and see if we can overflow a buffer. And then we can determine not only that the target address is reachable, but it's exploitable. So we could do something like that. Another thing that I already kind of mentioned was maybe multiple targets. You know, maybe there's a lot of string copies, which happens to be the case sometimes. And maybe we want to try and see if we can reach every single one of them. So we may just build a list of targets. And when we hit one target, iterate to the next target and start over and see if we can reach that one. If we can use part of the path, that's good. That's something to think about. So maybe we don't have to start all the way from scratch again. So multiple targets. That can generalize to a code coverage, because we can actually create a grouping of all the nodes, and we can just iterate through all of them as a target and see if we can reach 100% code coverage in the program. So there's a bunch of ideas to think about. So I know this is a lot of information that we got, especially with that theory and everything. And in an attempt to minimize questions, we're going to try and sum everything up. We made a nice little summary. So hopefully that answers most of your questions. It makes our job a little easier up front. But just in case that doesn't answer every single question you have, we'd be happy to take some of those now. What we're going to do is I'm going to actually meander through the crowd and visit people that have a question. And then I'll answer it if it's for me, or they won't answer it if it's for them. So if you have a little question, I'll just come over to you so everybody can hear the question for you. Yeah.
Yeah, I was curious as to how Sidewinder chooses its, or given a problem in an initial population. If you have to start out with an initial population, how do you choose that?
We'll let Ryan handle that. The initial population is just, there's not really any options to it.
You don't want to share that.
Is his not working? Did you hear that? How the initial population is chosen?
Sorry, the mic doesn't work up here. The initial population is just, what's up? The initial population is just chosen randomly, exactly as in the binary string example, but from variable length strings. So we just, we're choosing a bunch of integers at random of variable length.
But
Does that make sense?
over time, it's going to learn from that. You know, it's not going to keep that initial random population.
So there's absolutely no information basically going into the beginning.
Have you tried like simulated annealing approach to altering your mutation coefficient? Like start with a high and then varying it over time, letting it kind of.
We use dynamic mutation rate when our population starts to stagnate and we're not seeing any increase in fitness. And then as we make progress, then we slowly lower that mutation rate down again. Because obviously there's a compromise between preserving your existing information and generating new information.
Yes. Yes.
Hey there. So this looked pretty neat when it was restricted to a pretty simple protocol like a single packet that goes out. What about handshakes or more complicated protocols where you have a sequence of 4 or 5 packets, which represent quite a few of applications, especially the ones in my space?
We really haven't gotten to TFP.
To be perfectly honest, like I said, this is very prototypish. We think that the technology can be extended to handle protocols that would have some kind of state information, like a handshake protocol, but it doesn't do that right now. That's definitely an area of future work.
Yeah, because it even has the nice property that it will have a tendency to progress farther in the program as you get to farther in the protocol.
Yeah, we think that that could be an extension.
Add that to the grammar. You could actually add that to the grammar when you specify the grammar, the input string. So one could be the first handshake packet, the next handshake packet, and the next handshake packet.
Then one trick there is how you transfer the learning about the first packet, which is a unique thing to the second packet, because otherwise it would be kind of treated as a single two-piece packet.
Yes, it would be treated as, you know, one giant packet. What was that? Oh yeah, the idea of the dynamic grammar, actually learning the grammar on the fly would be very useful in that case.
Anybody else? Question? Yes.
Yeah. Would this also work with UDP packets? You mentioned it works with TCP. Would it work with UDP or any other protocols?
Well, the one program we're actually using is TFTP, which is over UDP. So that the internet protocol is really less important, I guess I would say. I don't know.
It should, in theory, pretty much work with any kind of protocol, except like what he's talking about with like where you have a handshake type, some kind of sequential information. However, you're going to have information in your program that you can learn from. So you're going to have something that's, you know, that's parsing out that protocol. Like I said, I mean, it's mostly useful for programs where you have a rich control flow structure. If you don't have anything to learn from in the program structure, it's not going to be very useful.
A few more minutes. Question? We'll get you and then we'll do you.
I was just curious, really quick, how you didn't mention what the runtime for the TFTP program one, and then the sort of corollary there is, did you do any other performance testing of like different, depending on the number of nodes in your call flow graph and or the key space of the initial values that you're looking for, what the runtimes were? I mean, what other sorts of simple tests had you done performance-wise on it? What was the runtime for the TFTP thing, first of all?
How long did it take?
Yeah. I guess to find the initial like valid packet, I guess was all you're really going for.
Yeah, it actually finds the runtime for the TFTP is hard because we didn't get the receive working correctly because of the router probably. So we're actually hacked in every breakpoint adds a little bit to a timer, and when the breakpoint stops, the timer expires, so it goes to the next one. So it's hard to say, but even with that, it seems like the TFTP is running a little faster than the keygen. And it could be a play on how many terminals there are in a grammar, or lots of other things.
What he asked about was like more complex protocols, things that, you know, code that has much deeper call graphs, and then larger key spaces. If you've got like you talked about a
to be perfectly honest, I mean, like I said, this is proof of concept. I mean, I think there's potential there.
It's really interesting. I don't want to.
I think there's potential there, but I mean, we haven't done anywhere near enough testing on enough complex programs at this point.
It seems like it might be something.
It's better than brute forcing, so it's still.
It seems like it's a little step in the right direction anyway.
Yes, sir.
You mentioned a Markov process in the theory part of the talk. Do you actually calculate probability on each edge of the core graph, or not quite sure how that's like?
Yes, it's Markov's memory list, so the fitness is calculated at each node. So if a genome goes down a path and it has 15, it'll actually calculate fitness for each edge it takes and multiply them all together. So
we're not actually calculating the probability strictly. We're viewing it as though we're sampling. So each time that we go through the process, the number of guys that go down that edge, we're estimating the probability. We don't actually know it. It would be very difficult to calculate exactly what it would be. Right.
I think we're running out of time.
I think our time's about up. If anyone has any further questions, we'll be available outside to chat, and then we'll be around, you know, tonight and tomorrow. Thank you.
You can find us at the pool tomorrow morning. Check.